And now we move to someone who's probably one of the most important figures in all of science, and that's Galileo Galilei. Galileo, who lived from 1564 to 1642, was a real experimentalist. People like Kepler were looking at observational data. Galileo also got his hands on real things. He purportedly dropped objects off the Leaning Tower of Pisa. Whether that's true or not, he certainly did experiment with terrestrial motion on Earth and tried to come up with an explanation and an understanding of how that motion behaved. He tried to answer the question and succeeded in answering the question, what's the natural state of motion on Earth? And Galileo did several things. We'll talk a little more later about his experiments with earthly motion, but he also did some observational astronomy, and he developed the first astronomical telescope. He was alive at the era when the whole idea of lenses for eyeglasses on vision correction had just been invented, and he made a telescope and he pointed it heavenward and he saw some things that had never been seen before. And I just want to describe for you three things Galileo saw, because they shook the foundations of this philosophical idea that the heavens up there were somehow perfect and different from the base and coarse and crude Earth down here. The first thing Galileo saw, not necessarily the first thing temporarily, but one thing he saw, we looked at Jupiter, and you can do this observation with a pair of binoculars. If you look at Jupiter, you'll see what Galileo saw. He saw four little dots lined up in a line on either side of Jupiter. You look in different nights, they're in different places. Sometimes you can't see one or two of them because they're behind or in front of Jupiter. But if you watch Jupiter when it's up in the sky at night, on different nights, you'll see these little dots that are in a line right across Jupiter's equator on either side of Jupiter. Those are the so-called Galilean satellites of Jupiter. They are clearly, and were clearly to Galileo, a kind of miniature solar system. They represented moons of Jupiter going around Jupiter in the same way the Earth's moon goes around the Earth. And so Galileo had for the first time an example of another solar system-like thing, another miniature cosmology. And it clearly had Jupiter at the center and the moons going around it. And that helped confirm the notion that there was nothing so special or unusual about the Earth being sort of like a moon of the sun, going around the sun along with all the other planets. By discovering another miniature solar system, if you will, Galileo had confirmed the Copernican idea that the sun was a solar system with the sun at the center and the planets going around it. It's a little bit, Galileo's discovery of Jupiter's moons, I think, is a little bit like what will happen when eventually, perhaps, we discover life somewhere else in the universe. We'll have a second example. All of a sudden, what happened here on Earth that many scientists don't think is unique will be proved not to be unique. Similarly, Galileo discovered the moons going around Jupiter, and for the first time, the solar system idea was not unique. It was a commonplace, or not commonplace, but at least it was a physical occurrence that had occurred more than once. So that was an important observation. The second observation Galileo made was of the phases of Venus. You're all aware of the phases of the moon. Sometimes it's full, sometimes it's new moon and you can't see it, sometimes it's a crescent, sometimes it's a half moon, sometimes it's gibbous, not quite full, and so on. Why does the moon have phases? Because the moon goes around the Earth, and at different times in its orbit, it's in a different place in relation to the sun. For instance, when it's a full moon, you'll notice the full moon rises at sunset. Why? Because the sun is on one side of the Earth, the moon is on the other side, and it's getting full sunlight. That's why the full moon always rises at sunset and always sets at sunrise, for example. At other phases, the moon is being hit. Only part of it is being illuminated. Only part of it you can see from Earth is being illuminated, and we get the phases. In the moon's case, although the moon goes through different phases, the phases are always the same size. Galileo observed the phases of Venus. Venus goes through full and crescent and so on. But there's something else that happens with the phases of Venus. When Venus is full, it's a very small circle. When Venus is a crescent, it's much larger. Why would that be? Well, there's an easy explanation for that in terms of the Copernican picture. In the Copernican picture, Venus is full when it's on the opposite side of the sun from the Earth. And therefore it's farthest away, and therefore it looks smaller. And it's a crescent when it's relatively near the same side of the sun as the Earth is, and the Earth is only seeing a small sliver of the lit up part of Venus, and therefore we see a crescent, and it looks much bigger because Venus is much closer. It would be very difficult to explain that observation in terms of the Aristotelian Ptolemaic idea that the Earth is at the center of the universe, because there Venus is going around the Earth, and except for that little circle on a circle, there's very little change in its distance from Earth. So the observation of the phases of Venus was a very important one in helping to verify the Copernican notion again that the Earth is not special. The Earth is not the center of everything. We're moving away from Earth-centeredness with that observation. The final observation that Galileo made, he looked at the sun and he observed sunspots. timing here, by the way, is remarkably lucky because the sun, very soon after Galileo's time, went into a phase called the Maunder minimum that we solar physicists, and I happen to be a solar physicist in my research field, we don't understand why that occurred, but the sun went through a period when it had almost no sunspots for a long time. What are sunspots? Well, to Galileo, they were dark blemishes on the surface of the sun. He hadn't actually discovered sunspots. The ancient Chinese had discovered them much earlier and called them crows and didn't know what they were, and Galileo didn't know either. But the important philosophical point was they were blemishes on the surface of the sun. Here's this celestial body, and it's no longer perfect. And by the way, you look at the moon, you see it has craters and mountains. It's not perfect either. Here's a break in the notion that the celestial realm is somehow perfect and not and somehow distinct from the terrestrial realm. All of a sudden there are mountains and craters and there are spots on the sun, and it's not perfect up there either. So why should it obey some kind of different perfect laws? Galileo didn't get any further than that, but he established the imperfection of the heavens, if you will, and that was a break in this notion of a separate terrestrial and celestial realm. Then Galileo turned to motion on Earth, and he did several important experiments. The experiment we're most famous with, the experiment in which he supposedly dropped objects off the Leaning Tower of Pisa, that was an experiment which, if it occurred, verified the notion that all objects fall toward the Earth with the same, not speed, but acceleration. They gain speed at exactly the same rate. It's a difficult experiment to do accurately. Air resistance gets in the way, but Galileo, if he did it from the Tower of Pisa, was able, by dropping objects of different weight, to confirm that they didn't fall at grossly different rates. That was an important understanding of gravity. Then Galileo carried out an important thought experiment, which I will describe here and show you in a visual. What Galileo did was to imagine a ball rolling in some kind of trough. Ball starts at some height in the trough, it rolls down to the bottom of the trough, and then it rolls up to the other side. And how far up would it get, Galileo asked. Well, he reasoned that if there were no friction and no air resistance and so on, everything were perfect, the ball would roll to the same height it started out at. And absent any friction or air resistance, it would simply roll back and forth in that trough continuously, back and forth, always rising to the same height. Of course, it doesn't. It eventually slows down because of friction and stops at the bottom. But that was Galileo's thought. So if you roll the ball from one side of the trough, it will rise to the same height on the other side. What if we make the other side of the trough somewhat longer? What if we take this trough, which is now symmetrical, and we stretch out one side of it? Well, the ball will still rise to the same height, reasons Galileo, in this so-called thought experiment. He didn't actually do this, but he said, what will happen if we did this? It will rise to the same height vertically, but it has to roll further horizontally to get there, because the trough that was initially symmetric is now longer on one side, the side it's going to rise up to after it rolls down. And then, said Galileo, what if we go one step further? What if we take that trough and lower it completely, make it horizontal at the bottom? So the ball rolls down the trough, and then it rolls continually horizontally along the bottom of the track. What happens? Galileo said, absent friction and air resistance, it never stops. Now, the historians of science will tell me I'm being a little bit simplistic here, and I am. Galileo was worried about the curvature of the Earth and other things like that. But in principle, this is the essence of his idea. Galileo said, if this trough never goes back up again, the ball will just continue rolling horizontally without its speed changing. And he reasoned that from this idea of taking the trough and gradually lowering the one side, the ball rolls farther and farther horizontally while rising to the same height. Finally, if it can't ever rise to the same height it started at, it will just continue to go horizontally forever. And Galileo therefore concluded something very, very different about terrestrial motion. He reasoned this way. He said, look, if an object is moving at a constant speed in a straight line, what's it going to do? It's going to keep doing that. It's going to move forever in a straight line at constant speed. It's never going to stop. That idea is crucial to classical physics and to modern physics as well. That idea is one of the key ideas in understanding motion. What Galileo is saying is the natural state of motion is not to be at rest on the surface of the Earth. That's a state of motion you get to because of things like friction and air resistance and things that you bump into like the floor when the ball falls. The natural state of motion is to move in a straight line at constant speed. It doesn't take a push to have something be moving. This is a crucial point. This is one we teachers of introductory physics spend a lot of time trying to get our students really to believe. It's really true, folks. It doesn't take any push to make something move. If you see something moving, the question is not why does it keep moving? The question might be, how did it get moving in the first place? Or if you see something that's stopped, how did it get stopped if it was earlier moving? The question is not what keeps it moving, because it takes no push, no pull, what physicists call a force. It takes no force to keep something moving. That's what Galileo says, and that's what appears to be a correct description of the way motion works. The natural state of motion is to be moving uniformly in a straight line. And there's a name for that statement. It's a name attributed to both Galileo and Newton. It's called the law of inertia. It says that an object has an inertia, a natural tendency to keep moving.